Hello, 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 ladies and gentlemen, and everybody watching this video. Welcome to this lecture. In today's episode, we are going to discuss about DC motors. So, in this lecture, we are going to deal with the principle of operation of DC motor and the classification of DC motor. So now let's start from the principle of operation. When you see the principle of operation, we have a stator and we have also the rotor. Both the stator and the rotor have got winding, except for permanent magnet motors. We don't need to have a stator winding because we are going to use a permanent magnet. So in that case, the stator winding is not needed. So the purpose of this winding, the stator winding or the field winding, is to produce a magnetic field. Here, the rotor is supplied by a DC power supply, maybe from separate DC source or a battery, or might be connected to the stator one. You know that this winding is made up of copper, and copper is a non-magnetic material, so nothing to do with the magnet. But whenever you apply a current to this copper winding, now this current will produce a magnetic field around, according to the Ampere's law. So this produced magnetic field around the current carrying conductor will interfere with the magnetic field produced by the stator. So definitely there is a force, might be attraction or repulsion, that can be occurred between the stator and the current carrying conductor or the armature. So this force makes the rotor to spin or to rotate. So this is the principle of DC motor. Now, DC motor is considered to be one of versatile and or adaptable and flexible machine. That means you can easily vary the speed of DC machine by simply varying the resistance, which is inserted in series with the armature, that's known as rheostat. So it is considered as adaptable, versatile, or flexible machine. And DC machines are most commonly used for high starting torque applications, for high accelerating and decelerating torques, and it's also used for a wide range of frequency control applications. So the major advantage of DC machine is speed control is not as such a big deal like a case of AC machine, but here you can easily control the speed of the machine by varying the resistor or by varying the voltage. And torque regulation is as such easy. So we have also these days large amount areas of application of DC machines, like vehicles, airplanes, ships, locomotives, movable electronic mills and mines, and so forth. We have a lot of application of DC motors these days. And this was the principle that I've already stated at the introduction part. So this is a stator part, which is responsible to produce a magnetic field. And this is armature, which is a current carrying conductor and also will produce a magnet around this. So this, the magnetic field produced by the armature and the stator will interact and produce a force that is known as Lorentz force. And of course, this force depends on the magnetic field of the stator, the field magnetic field density. This is magnetic field density, and the length of the conductor, the length or the number of turns of the conductor, and the amount of applied current to that conductor. So these are directly proportional with the amount of induced force. And the direction of the force is again can be obtained by Fleming's right-hand rule. I mean left-hand rule. The right-hand rule was for the generator, and here it is left-hand rule. And here is the types of DC motor, like a DC generator. We have 3 types of DC motors: separately excited, self-excited, permanent magnet DC motors, in which the stator part is made up of permanent magnet. On the self-excited, again, further classified into shunt, series, and compound, and the compound again can be further classified. So let us see those classification one by one. In today's video, we are going to cover the permanent magnet and the separately excited one, and we'll proceed the self-excited in another video. So yeah, here as you can see, this is a permanent magnet DC motor, and there is no any winding on the stator, as you can see here. So it is replaced by a permanent magnet. So this permanent magnet will responsible to produce a magnetic field. Well, this is a rotor which is wound and supplied with the DC power supply or DC current or DC voltage, or through the slip rings and through the brushes. So we cannot directly supply the winding of the armature directly with the power supply. So because this is a dynamic one which is rotating, so it's difficult. So in that case, we have to give supply through the stator one, which is through brush and to commutator and to the rotor. And the second part is separately excited. In this case, we have a separate DC battery or DC voltage source for the stator part, and we have another DC source for the rotor part. So we have separate 2 DC power supplies, one for the stator and one for the rotor. So in this lesson, we are going to see the analysis of, and we have to see some of the starting methods, and we will see the characteristics of the separately excited DC motors. Well, this is the equivalent circuit of separately excited DC motor. As you can see, this is a separate DC power supply, and again we have another separate DC power supply for the armature. This is for the field. And since the 2 circuits are separate, so it's very difficult to make analysis of the 2. But from the from the basic knowledge of the machine, we can characterize we can drive some of the equations. Like, for instance, in the field, as you can see, this is a field circuit. We have a resistance and inductance of, this is actually due to the winding of the field winding. So we have inductor and resistance, of course, but this inductance, as you know, the inductive reactance XL highly depends on the frequency 2 pi F and L. So, but in DC, the frequency is 0, hence this quantity will be 0, or the resistance of the impedance of the inductance will be 0. That means it's a short circuit. So we have to consider only RF. Therefore, the current IF equals VF divided by RF. And when you come to here, this is a complete circuit. Again, the same is true here. The armature inductance will be short circuit because of a DC analysis, but in case of AC analysis, we have to consider inductance. But this is a DC circuit analysis. So in this case, we have to omit the inductance value. And so VA, the armature voltage, equals EA, the back EMF, plus IA times RA, the voltage drop across the winding. And always EA, the back EMF, depends on the speed of the machine. At the speed of the machine increase, the back EMF also increase. So back EMF depends on the machine constant, of course, the amount of the strength of the magnetic field in the stator, IF, and it depends on the speed of the machine. And the torque, since this is a motor, we have to strictly focus on the speed and torque, because these are the two outputs, and voltage and current, armature voltage and armature current are the inputs. So the torque is depend on the machine constant again, and the armature current, and also the amount of magnetic field. That means amount of IF, or field current. So from this, yeah, you can consider this equation. From this equation, you can drive the speed. You can drive the speed, because when you drive the speed equals EA, back EMF, divided by K times IF, or the field current. So omega equals EA divided by KIF. But EA, from this equation, you can drive EA, yeah, EA equals VA minus IARA. So instead of EA, I can replace VA, RA. So from this, we can observe that the speed of a separately excited DC motor depends on the amount of armature voltage, the amount of armature current, the amount of armature resistance, or armature winding resistance, and it depends on the amount of machine constant, and it depends on the field current. So these are the variable on which the machine depends. From this, yeah, this is constant, RA is constant. You can't, unless and otherwise you seriously insert a resistor, you can't vary RA, it is constant. And VA is also constant. So most of the variables are constant here. And the speed of separately excited machine, when we see in terms of IA, you can develop the speed versus VA, speed versus IA curve. So from this, we can generally say that speed of a separately excited DC motor can be varied by two ways, or two methods. The first one is by varying the armature part, I mean armature current, or armature resistance, or armature voltage, and the field part, it can be field voltage, or can be field current, or can be, of course, field resistance, but these are mostly constant. So by doing this, we can control the speed of separately excited machine. So generally, there are two ways of varying the speed in general expression. These are either varying the field voltage, or by varying the armature voltage or armature parameters. So this can be implemented in two ways. The first one is to vary the voltage. We have to use a variable voltage like auto transformer. This is one possibility. The other possibility, and most commonly used, is we have to use a variable resistor, which is called rheostat. So we insert a rheostat in series with the field, as well in series with the armature. So you can choose one of the two ways. So you can insert a variable resistor
in series with the armature coil, or you can insert a variable resistor rheostat in series with the field winding. So by adjusting this, definitely you can adjust the input, the voltage drop across the windings.
Let us see the starting method of separately excited DC motor. So from this basic equation, as you can see here, IA equals VA into K flux omega RA. So from this, IA depends on armature resistance, but this armature resistance is mostly, it is a very small value. Since this value is very small or very minimum, so IA is mostly assumed to be high. And at starting, always, since the speed and the flux are almost zero, so especially the speed is zero. If the speed is zero, this quantity will be zero. So IA will significantly increase. And most of the time, at the starting, the value of IA can be in the order of 200% to 800% of the rated current. So if we allow this current to flow through the machine, and the machine will be burned out. So always when we start a separately excited DC motor, we have to start with a very low voltage, low input voltage, or we have to insert a series resistor or rheostat which is connected to the armature. Unless and otherwise, if you directly give a rated voltage and start a separately excited DC motor, the machine might be damaged, or the overcurrent may overheat the motor, and it might be burned out the machine. So it's very serious. So in general, what we can say is at starting of separately excited DC motor, we have to start with a very low voltage. Say if the rated voltage is 200 volt, so we can start with say 20 volt and slowly increase to 50 volt and slowly increase to 100. And when the machine once reached to the rated speed, we can put the voltage to the rated voltage, that is 200 volt. Or mostly we might not have a variable voltage, or we might not have auto transformers. So in that case, we can insert a rheostat, resistors, a variable resistor in series with the armature, and we can apply the rated current, rated voltage to the armature. And always be sure that when you start the motor, the rheostat should have to be at a maximum resistance, so that the amount of voltage drop in the rheostat will be higher and the amount of voltage drop in the machine will be lower. So in that case, the machine will experience low voltage, so the armature current will be lower. And slowly you can decrease the resistance, the series resistance of the rheostat, and then the amount of voltage drop in the rheostat will be minimum, and the amount of voltage drop in the machine will be increasing. Then once the machine reach the rated speed, then you can automatically make the rheostat resistance to 0 or to the minimum. So with this, we can start the separately excited DC motor.
When the torque increase, the speed will decrease. The speed will decrease. So seems something like a constant curve, but it's not exactly constant, but with it is decreasing with some slope. with the slope of RA divided by KIF square. So this is a torque speed characteristics of separately excited DC motor. So at any torque, the speed is almost constant. Therefore, it is used for constant speed application like electric traction. So with this, we'll end our today's lesson. And thank you for watching. And don't forget to subscribe, like, and write a comment. I will meet you with another video next time. See you. Have a nice time. Bye-bye.